So for C, we have a length of 448, okay, some wire that's 448 long. And we have another length that's 616 centimeters long. And we want to know that these are going to be cut into pieces, all the same length, and we want to know what's the largest length so that the pieces are going to have all share the same length. Okay, well, it looks like I need to break this up into pieces so that we're talking about factors here, right? We're not growing these numbers, we're breaking this number into groups, basically. So my 616, okay, when I factor that, I'm going to do a little factor tree over here. Okay, I'm going to end up with, that's going to be 308, 154. Okay, it's going to be 77, 7 and 11. Okay, so this is going to end up being 2 times 2 times 2 times 7 times 11. Okay, and then 448. We're going to factor this as well, so I'm going to use the factor box here. So 2, that's going to be 224. 2 again is going to be 112. 2 again is going to be 56. Okay, 2 again is going to be 28. 28 is going to be 2 and 14. 2 and 7. 2 and 7. Okay, so we end up with 1, 2, 3, 4, 5, 6, 6, 2. So 2 times 2 times 2 times 2 times 2 times 2 times 7. Okay, so the greatest common factor then, of these, we're going to end up with 2's, 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 and 1, 7. So we have 2 times 2 times 2 times 7, which is going to be 56. Okay, so we can break this up into 56 centimeter lengths, and it will divide both of those wires evenly. Okay, we won't have any leftovers if we break that into 56, and that's the longest pieces that we can use. Right? I mean, we could always just do 1 centimeter pieces, but we want the biggest length that we could use. Okay, here Jasmine are each given piece ribbon of equal length. Jasmine cuts her ribbons into equal lengths of 22. Jasmine cuts her into equal lengths of 15. Okay, so let's just sketch a little picture here. So this is going to be Janice. Okay, and she gets some length here. And hers are going to be, Janice is into 22, so she goes 22, 22, dot, 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 dot. Okay, so Jasmine has exact same length of ribbon, but she's going to cut hers into shorter pieces. 15, okay, 15, 15. So there's no remainder, so they cut all the way to the end here. They both end up at the exact same length. Okay, but one is doing it in groups of 22, the other one's doing in groups of 15, and we want to find the shortest possible length of ribbon to give them. Okay, the shortest possible length is going to be the shortest multiple, so we want really the lowest common multiple here. Okay, so this is an LCM problem. So if I want to find the LCM of these, I can skip count and just count until I get to the same one. I'm going to use our prime method because a prime method is fairly efficient. Okay, so this is going to be 3 times 5. Okay, so 22 and 15 share no common factors. Okay, so in order to make them the same multiple, this guy needs all the factors here, and this guy down here needs all the factors from the top. Okay, and when we do that, we're going to end up with 22 times 15, so that's going to be 300 and, I think that's 330. Yeah, 330. Okay, so the LCM works out to be a length of 330 centimeters. Okay, so that we can make groups of 15 with 330, we can make groups of 22 with 330. So that must be the lowest common multiple, or the shortest length of ribbon that we could have used to make both sets of ribbons. Okay, so this one we have a racing track, and just going to sketch out a track here. So there's my straightaways, and let's make this an oval track. Okay, so we know that one guy gets around in 28 seconds, the other guy gets around in 24 seconds. So you can kind of maybe think of it this way. We have the starting point here at 24. It's going to be a little bit difficult to show actually, but they both starting, we'll call car A and car B. Okay, they're both going around the track. So going to be different speeds. So basically, when do they end up back at the start at the same time? So they're going to be back at the start. Well, after 28 seconds, this guy's 4 seconds ahead. And basically, he's got to catch up. The 24-second guy has to catch up for 20 seconds, 20 more seconds to get around. So after one lap, they're 20 seconds behind. After 2 laps, he's 16 seconds behind. After 3 laps, he's catching up 4 seconds each time to lap the other person. 12 seconds. 4th lap, he's going to only be 8 seconds behind. 5th lap, he's going to be 4 seconds behind. And on the 6th lap, he's going to catch him, and they're going to be at the same point. Okay, so they're going to catch each other right at that 6th lap. Okay, so the answer to this, how many seconds? Well, this is the 6th lap of this guy here. Okay, so because this guy's only done 6 laps, this guy would have done 7 laps. So we can also do this problem using, this is really just multiples. When are the multiples going to end up being the same time? So we can think of this as 28 seconds. Okay, it's going to be 2 times 2 times 7. And for 24 seconds, it's going to be 2 times 2 times 2 times 3. And the smallest multiple is going to be, well, we're just going to take all the common factors. Okay. And so I'm just doing it slightly differently than I did the last one. So this is an LCM problem, right? First of all, let's make sure with that. We're going to take one of these. Oops. It's going to be 2 times 2 times 2 times 3 times 7. So basically, we need to make sure that this guy on the bottom has all the multiples, all the factors involved on the top, and the guy on the top needs to have all the factors from the bottom. Okay, so just clean that up a little bit. That's going to be times 2 times 3. Okay, so then these all going to match. So we're going to end up with 24 times 7, which is 168 seconds. Okay, and that represents the lowest common multiple of this problem of 24 seconds and 28 seconds.